In the cold, crystalline vastness that lies beyond Neptune, a region of the solar system stretches out, silent, enigmatic, and barely touched by the warmth of the sun. Here the Kuiper Belt, a great disk of icy debris and ancient relics, spins in a slow ballet. For decades, astronomers believed they had mapped the principal actors in this remote domain, counting the dwarf planets and scattered comets as the final echoes of planetary formation. But in the early years of the 21st century, whispers began to ripple through the astronomical community. Rumors of a gravitational ghost, a hidden giant lurking in the outer dark, its presence betrayed not by a glimmer of light, but by the subtle, persistent tugs it exerted on the orbits of smaller worlds. They called it Planet 9, a hypothetical planet, massive and distant, whose existence, if confirmed, would reorder our understanding of the solar system's architecture. Tonight we journey into the heart of this mystery, following the evidence, the skepticism, and the dreams of those who seek a world unseen. It begins, as so many stories do, with an uneasy question. Why, out beyond Neptune, do certain objects trace such peculiar, elongated orbits, as if some unseen hand were shepherding them into position? In 2016, astronomers Konstantin Batygin and Mike Brown of the California Institute of Technology published a paper that electrified the field. By analyzing the orbits of 6 distant Kuiper Belt objects, or KBOs, they noticed a strange alignment. The long axes of these objects' orbits all pointed in roughly the same direction, as if they were marching in lockstep. This was not something that could be easily explained by the known planets. The odds of such a pattern arising by chance were vanishingly small, less than 0.007%, they calculated. Batygin and Brown proposed a solution as audacious as it was profound. A 9th planet, perhaps 10 times the mass of Earth, lurking hundreds of astronomical units from the Sun, its gravitational influence subtly but inexorably shaping the outer solar system. To appreciate the magnitude of this hypothesis, it is worth recalling the solar system's known order. 8 planets, from Mercury's sun-baked surface to Neptune's azure clouds, orbit the Sun in near-circular paths, a cosmic clockwork whose motions have been catalogued since the days of Kepler and Newton. But the outer solar system, beyond Neptune's orbit, at 30 astronomical units, or AU, from the Sun, is a realm of uncertainty. Here, dim dwarf planets like Eris, Haumea, and Makemake drift in slow, frozen arcs, their discovery only possible thanks to advances in digital imaging and the relentless patience of sky surveys. The Kuiper Belt extends from roughly 30 AU to 50 AU, but beyond even this lies the mysterious scattered disk, home to objects like Sedna and 2012 VP-113, whose orbits stretch hundreds, even thousands of AU into the deep. The gravitational environment in these reaches is poorly understood. Minor nudges by passing stars during the Sun's birth cluster, the cumulative effects of galactic tides, and the gravitational pull of the giant planets all play a role. Yet the peculiar clustering of the most distant KBOs seems to demand a more powerful sculptor, a planet perhaps whose mass is sufficient to corral these small bodies over billions of years. The search for unseen planets is a recurring motif in the history of astronomy. In the 19th century, irregularities in Uranus's orbit led to the prediction and eventual discovery of Neptune in 1846, a triumph of Newtonian mechanics and international collaboration. Later, the search for a hypothetical Planet X, thought to explain further anomalies, led Clyde Tombaugh to discover Pluto in 1930, only for later measurements to reveal that Pluto was far too small to fulfill the predictions. Instead, improved observations showed that the supposed irregularities were the result of errors in the measured masses of Uranus and Neptune themselves. Yet the allure of hidden worlds, of the unknown lurking just beyond the edge of the map, never faded. Batygin and Brown's proposal reignited this ancient longing. The evidence, though circumstantial, was tantalizing. Not only were the orbits of distant KBOs clustered in orientation, but their perihelia, the points of closest approach to the Sun, were also confined to a narrow region of the sky. Simulations showed that a planet with a mass between 5 and 15 Earths, following an elongated orbit with a semi-major axis between 400 and 800 AU, and an eccentricity perhaps as high as 0.6, could naturally produce the observed patterns. Such a world would take between 10,000 and 20,000 years to complete a single orbit around the Sun. Its distance, and its possible inclination of 15 to 25 degrees to the ecliptic would render it almost invisible to existing surveys. Its light, a faint pinprick lost among the countless stars. But the search for Planet 9 was not merely a matter of celestial mechanics. It was also an odyssey of technology and perseverance. The sky is vast, and the region to be searched, even after accounting for dynamical constraints, covers thousands of square degrees. The planet's expected brightness, given its assumed size and albedo, would be no greater than magnitude 22 or 23, comparable to the faintest galaxies visible to the largest ground-based telescopes. To find such a world requires not only sensitive detectors and clear skies, but also clever data processing, capable of distinguishing the slow drift of a planet from the static background of distant stars. Astronomers marshaled their resources. The dark energy camera, mounted on the Blanco 4-meter telescope in Chile, was pressed into service, as was the Subaru telescope atop Mauna Kea in Hawaii, whose wide field and sensitive optics made it ideal for searching the outer solar system. Automated sky surveys such as Pan-STARRS and the Catalina Sky Survey combed the heavens for moving objects, their algorithms scanning billions of pixels for the faintest hints of motion. Each candidate detection had to be painstakingly confirmed, its position measured over multiple nights to rule out false positives, cosmic rays, asteroids, or variable stars masquerading as planets. As the search unfolded, astronomers found themselves drawn into a deeper, more philosophical debate. Was the evidence for Planet 9 truly compelling? Or was it an artifact of small-number statistics and observational bias? The objects whose orbits seemed to cluster so mysteriously were few in number, only a dozen or so at first, rising to a couple dozen as new discoveries trickled in. Could it be that telescopes, focused preferentially on certain patches of sky, had simply missed the full population? Some researchers, like Alessandro Morbidelli in Nice, France, and Michel Bannister in the United Kingdom, argued that the apparent alignment might be a mirage, the result of complex selection effects. The stakes were high. To claim the existence of a new planet on the edge of the solar system was to stake a claim on the very map of the cosmos, to redraw the boundaries of the known. Yet the evidence continued to mount, though never definitively. Several independent groups, including those led by Scott Shepard and Chad Trujillo, reported the discovery of additional distant objects whose orbits echoed the predicted patterns. Sedna, discovered in 2003 by Brown, Trujillo, and Rabinowitz, was the first of these, its perihelion at 76 AU, far beyond the gravitational reach of Neptune. 2012 VP-113, nicknamed Biden, followed in 2012, with a perihelion of 80 AU. Together with a handful of other extreme trans-Neptunian objects, ETNOs, these worlds formed a ghostly procession, their orbits elongated and tilted as if caught in the invisible wake of a distant planet. Batygin and Brown, ever cautious, refined their models. They showed that a planet of roughly 10 Earth masses, on a moderately inclined and eccentric orbit, could not only explain the clustering of ETNOs, but also account for the existence of high-inclination TNOs, objects whose orbits are tilted at angles greater than 40 degrees to the ecliptic, and even some whose orbits are retrograde, circling the Sun in the opposite direction from the planets. The gravitational influence of Planet 9, they argued, would naturally excite such orbits over billions of years, providing a unified explanation for a diverse array of phenomena. But the search for Planet 9 also forced astronomers to confront the limits of their knowledge. The outer solar system is a realm of deep time, where the slow, cumulative effects of gravity play out over aeons. Small nudges from passing stars, tidal forces from the Milky Way, and the chaotic interactions of the known planets can all shape the orbits of distant objects. To disentangle these influences requires not only detailed observations, but also massive computer simulations, models that track the motions of thousands of bodies over the 4.5 billion-year history of the solar system. In this effort, astronomers drew upon the power of modern supercomputers. Teams at institutions like the Southwest Research Institute and the Observatoire de la Côte d'Azur crafted intricate N-body simulations, mapping the long-term evolution of the Kuiper Belt under a variety of scenarios. In some models, Planet 9 shepherded the orbits of distant objects into neat, aligned patterns, just as observed. In others, Alternative explanations, such as a massive disk of small bodies or the cumulative effects of multiple smaller planets, were tested and found wanting. Yet the simulations also revealed the fragility of the evidence. Small changes in the assumed parameters of Planet 9 or in the initial distribution of KBOs could produce wildly different outcomes. The search became a game of probabilities, a dance between theory and observation, where certainty was always just out of reach. The question naturally arose, if Planet 9 exists, where did it come from? The solar system's history is a tale of violence and migration, of giant planets forming in a swirling nebula and then scattering under the influence of mutual gravitation. Some theories suggested that Planet 9 might be a primordial ice giant, formed in the inner solar system, and later flung outward by interactions with Jupiter or Saturn. Others proposed a more exotic origin, a rogue planet, captured from another star during the Sun's birth cluster, now bound to our solar family by the faintest of gravitational threads. Each scenario carried its own implications for planetary formation, migration, and the architecture of planetary systems throughout the galaxy. The technical challenge of actually finding Planet 9 was daunting. At an estimated distance of between 400 and 800 AU, the planet would be so faint as to escape detection by all but the most sensitive instruments. Its apparent motion across the sky would be glacial, just a few arcseconds per hour, nearly indistinguishable from the background stars. And the sheer size of the search area, tens of thousands of square degrees, even after accounting for dynamical constraints, meant that every night of telescope time was precious, every observation a needle in a cosmic haystack. Yet astronomers pressed on, driven by the hope of discovery. In 2017, the Zwicky Transient Facility at Palomar Observatory joined the search, its wide-field camera capable of imaging hundreds of square degrees each night. The Vera C. Rubin Observatory, expected to begin operations in the mid-2020s, promised to revolutionize the hunt with its unprecedented sensitivity and sky coverage. Some dreamed that the James Webb Space Telescope, with its infrared eyes, might one day catch a glimpse of the planet's faint thermal glow, a ghostly ember in the cold of interstellar space. As the years passed, the search for Planet 9 became a crucible for the scientific method itself. The hypothesis was bold, yet falsifiable. If the planet exists, it should be found. If not, its absence would require a rethinking of the evidence. Teams around the world redoubled their efforts to survey the sky, to discover new etnos, and to refine the models that linked their orbits to the presence of a hidden giant. The stakes were high, not just for planetary science, but for our understanding of the processes that shape the solar system, and by extension, planetary systems throughout the galaxy. Yet even as the search continued, alternative explanations for the observed patterns gained traction. Some astronomers proposed that a massive disk of small bodies, rather than a single giant planet, could produce the clustering of KBO orbits. Others suggested that the observed alignments might be the result of observational bias. Telescopes tend to survey certain regions of the sky more intensively than others, and the discovery of etnos depends sensitively on the geometry of their orbits relative to Earth. In 2017, a team led by Corey Shankman and Michelle Bannister published a study arguing that the evidence for clustering was not statistically significant once these biases were taken into account. The debate sharpened, with advocates of the Planet 9 hypothesis responding in kind, refining their models and calling for more data. The search thus entered a new phase, a race between discovery and doubt, evidence and interpretation. Each new etno, each faint smudge on a CCD image became a piece in an intricate puzzle, its orbit mapped and analyzed for signs of hidden influence. At conferences and colloquia, astronomers debated the merits of the Planet 9 hypothesis, the room crackling with the energy of scientific contention. For every skeptic who pointed to the dangers of confirmation bias and small number statistics, there was a champion who argued that the patterns were too persistent, too improbable, to be dismissed as chance. In the background, the solar system continued its ancient dance, the planets and comets tracing their paths through the void. The search for Planet 9 became a lens through which astronomers viewed not only the outer reaches of our planetary system, but the very nature of scientific discovery. It was a story of perseverance in the face of uncertainty, of the slow, patient accumulation of evidence, and of the willingness to question even the most cherished assumptions. The drama of the search was heightened by the tantalizing possibility of discovery. What would it mean to find a new planet? A true giant lurking on the edge of the solar system? The implications would be profound. A planet 10 times the mass of Earth would rival Uranus and Neptune in scale, though colder and darker by far. Its surface, if it had one, would be frozen and bathed in eternal night. Its atmosphere perhaps a thin layer of hydrogen and helium laced with methane and ammonia. Any moons it possessed would be ancient and battered, relics of a primordial age. The discovery would rewrite textbooks, inspire a new generation of missions, and challenge our understanding of planetary formation. But the search for Planet 9 was also an exploration of the boundaries of human knowledge. The distances involved defy easy comprehension. At 600 AU, the planet would be 20 times farther from the Sun than Neptune, its years stretching across the ages. The light that left its surface would take more than 3 days to reach Earth. The challenges of navigation, communication, and propulsion for any future spacecraft mission are staggering, yet not beyond the dreams of engineers and scientists. Concepts for nuclear-powered probes, laser sails, and even gravitational slingshots have been proposed, each a testament to the audacity of human curiosity. As the search pressed on, astronomers found themselves drawn into a deeper reflection on the nature of discovery itself. The history of astronomy is a chronicle of expanding horizons, of worlds revealed by ever more sensitive instruments and ever more ambitious theories. From the first recognition of the solar system as a collection of planets orbiting the Sun, to the discovery of Uranus by William Herschel in 1781, Neptune by Urbain Le Verrier and Johann Galle in 1846, and Pluto by Clyde Tombaugh in 1930, each new world has carried us a step further from the center, a step deeper into the unknown. But the search for Planet 9 is different. It is not the story of light, but of shadow, of a planet inferred by its absence, glimpsed only through the subtle fingerprints it leaves on the orbits of distant objects. It is a search conducted not in the visible spectrum, but in the realm of mathematics, simulation, and inference. It is, in a sense, a return to the earliest days of astronomy, when the heavens were mapped not only by what could be seen, but by what could be imagined. The mystery of Planet 9 is also a story of community, a testament to the collaborative, cumulative nature of science. Observatories from Chile to Hawaii, from Arizona to the Canary Islands, have contributed their time and talent to the search. Graduate students and veteran astronomers alike have spent long, cold nights at the eyepiece or the computer terminal, sifting through data in search of the faintest hint of motion. The search has drawn in specialists in celestial mechanics, computational astrophysics, observational astronomy, and planetary science, each bringing their own insights and expertise to the problem. There are moments of frustration, each promising candidate that turns out to be an asteroid, each night lost to clouds or technical failure, each simulation that diverges into chaos. But there are also moments of wonder, the discovery of a new etno, the realization that a pattern glimpsed in the data may hold the key to a larger truth, the sense of standing on the threshold of discovery. The search for Planet 9 has also sparked a renaissance in the study of the outer solar system. As astronomers have scoured the skies for signs of the hidden planet, they have discovered dozens of new KBOs, each with its own unique story to tell. Some, like 2015 TG387, dubbed the Goblin, have orbits that stretch nearly 1,000 AU from the Sun, their distant paths shaped by forces yet to be fully understood. Others, like 2004 XR190 or Buffy, challenge existing models with their high inclinations and odd eccentricities. Each new object adds a brushstroke to the portrait of the Kuiper Belt, revealing a system more dynamic and diverse than once imagined. The search has also illuminated the connections between our solar system and the wider galaxy. Astronomers have come to realize that planetary systems are not static, but dynamic and evolving. The discovery of thousands of exoplanets, many on eccentric or inclined orbits, some as massive as Jupiter, others as small as Earth, has forced a reevaluation of the processes that govern planetary formation and migration. In this context, Planet 9 is not an anomaly, but a bridge, a link between the familiar worlds of the inner solar system and the wild diversity of exoplanetary systems beyond. The search for Planet 9 has also raised profound questions about the nature of observation and inference. In astronomy, as in all the sciences, there is a delicate interplay between theory and data, between what is seen and what is expected. The orbits of distant KBOs are like footprints in the snow, their patterns hinting at the passage of a hidden traveler. But footprints can be misleading, shaped by wind and weather, by the complex interplay of many forces. To claim the discovery of a new planet on the basis of such evidence is to walk a narrow path between insight and illusion. Yet it is precisely this tension that gives the search its power. The history of science is filled with examples of worlds inferred before they were seen, of phenomena predicted by theory and later confirmed by observation. The discovery of Neptune, guided by Leverrier's calculations, is perhaps the most famous example. But there are others. The existence of black holes predicted by the equations of general relativity long before the first candidate was identified. The cosmic microwave background, anticipated by Big Bang theory years before Penzias and Wilson heard its faint echo in their radio receiver. In the case of Planet 9, the balance between theory and observation is particularly delicate. The evidence is circumstantial, statistical, and evolving. Each new discovery has the potential to tip the scales, to confirm or refute the hypothesis. The process is slow, incremental, and at times frustrating, but it is also deeply human, a testament to our capacity for patience, imagination, and wonder. As the search enters its third decade, the pace of discovery shows no sign of slowing. New surveys, new telescopes, and new computational techniques promise to extend our reach deeper into the dark. The Vera Rubin Observatory, with its 10-year legacy survey of space and time, LSST, will scan the entire southern sky every few nights. Its 3.2 gigapixel camera capturing faint objects that have so far eluded detection. The James Webb Space Telescope, now stationed at the L2 point a million miles from Earth, offers the possibility of detecting the faint infrared glow of a distant planet, its heat signature lingering long after the last rays of sunlight have faded. The search for Planet 9 is not merely an exercise in planetary astronomy. It is a window onto the processes that shape planetary systems, a probe of the solar system's earliest history, and a test of our capacity to perceive the unseen. If the planet is found, it will be a triumph of inference and persistence, a new chapter in the story of the solar system. If not, the search will have revealed new mysteries, new questions, and new worlds in the outer dark. The mystery of Planet 9 also serves as a mirror, reflecting the limitations and aspirations of human knowledge. In the darkness beyond Neptune, we confront the limits of our instruments, the biases of our observations, and the uncertainties of small-number statistics. We are reminded that science is not a linear progression from ignorance to certainty, but a journey through ambiguity, error, and revision. Each new discovery brings not only answers but new questions, new frontiers, and new horizons. As the search continues, astronomers are also exploring new avenues for detection. Some have suggested that Planet 9, if it exists, might be detectable through its gravitational influence on spacecraft in the outer solar system. The trajectories of Voyager 1 and 2, New Horizons, and Pioneer 10 and 11 have been monitored for subtle deviations that might betray the presence of a distant planet. So far, no definitive evidence has emerged, but the search continues. Others have proposed more exotic methods. The planet's passage in front of a distant star could, in principle, produce a brief occultation, a momentary dimming that might be detectable with sensitive photometry. Its faint thermal emission, in the far infrared or submillimeter range, might be picked up by future space-based observatories. Theoretical studies have explored the possibility that Planet 9 might even be a primordial black hole, a remnant from the earliest moments of the universe, though this scenario is considered unlikely by most researchers. The search has also inspired a new generation of citizen scientists. Projects like Backyard Worlds, Planet 9 invite the public to sift through telescope images, searching for the faint, slow-moving dots that might signal the presence of a new planet. In this way, the search for Planet 9 has become a global endeavor, drawing on the collective curiosity and ingenuity of people around the world. The quest for Planet 9 is, in the end, a story of perseverance in the face of uncertainty. It is a testament to the power of prediction, the value of skepticism, and the enduring allure of the unknown. Whether the planet is ultimately found or not, the search has already transformed our understanding of the solar system, revealing a world of complexity, dynamism, and wonder, far beyond what was once imagined. It is also a story of humility. In the darkness beyond Neptune, we are reminded of how much remains unknown, how much lies beyond the reach of our current instruments and theories. The solar system, once thought to be a closed and orderly system, is revealed as a frontier, dynamic, evolving, and filled with surprises. The search for Planet 9 is a reminder that the universe is vast, that our knowledge is provisional, and that the spirit of exploration endures. If Planet 9 exists, its discovery will stand as a testament to the power of inference, the value of persistence, and the wonder of the unknown. If not, the search will have illuminated new mysteries, new questions, and new worlds in the outer dark. Either way, the journey itself is its own reward, a testament to the enduring power of curiosity, imagination, and the human spirit. Tonight, as we gaze into the darkness beyond Neptune, we are reminded that the universe is not only stranger than we imagine, but stranger than we can imagine. The search for Planet 9 is a story not only of planets and orbits, but of the human desire to know, to explore, and to understand. It is a story that will continue, as long as there are eyes to see, minds to imagine, and hearts to wonder. The cold reaches of the outer solar system remain for now a frontier, a place where the known dissolves into the unknown, where each new discovery invites 1,000 new questions. In this realm, the search for Planet 9 is both a quest for a hidden world and a meditation on the nature of discovery itself. It is a journey into the heart of darkness, into the silence beyond the last planet, where the faintest glimmers of light and the subtlest whispers of gravity hold the promise of revelation. As astronomers continue their search, mapping the orbits of distant KBOs, refining their models, and scanning the skies for the faintest trace of motion, they are engaged in an act of faith, a belief that the universe, though vast and indifferent, is ultimately knowable, that its secrets can be uncovered by patience, ingenuity, and imagination. It is a belief that has sustained generations of explorers, from the earliest stargazers to the scientists of today. The search for Planet 9 is a story without an ending, a journey without a map. It is a reminder that the frontiers of knowledge are always receding, that each new discovery opens up new vistas, new questions, and new mysteries. It is a testament to the power of wonder, the value of skepticism, and the enduring allure of the unknown. In the darkness beyond Neptune, a hidden planet may await discovery, a world 10 times the mass of Earth, tracing a slow orbit through the outer dark. Or perhaps the mystery will prove more subtle, the patterns more complex, the explanations more elusive. But whatever the outcome, the search itself is a testament to the human spirit, a celebration of curiosity, imagination, and the enduring quest to know our place in the cosmos. The story of Planet 9 is, in the end, a story of possibility, a reminder that the universe is vast, that the unknown beckons, and that the search for knowledge is an endless, ever-renewing journey. In the silence of the outer solar system, beneath the pale light of distant stars, the mystery endures, inviting us onward, ever deeper into the dark.